Hey everyone. In this video, I'm going to begin our discussion of how to model dichotomous outcome variables by introducing the linear probability model, which is basically just applying OLS to a problem where your outcome measure is indeed dichotomous. Okay. So to get started, there are a couple of different ways we can model binary outcomes or binary responses. And this is really important because there are many outcomes in social science and the political sciences that are binary, where we only have two discrete outcomes that we can measure, right? And this goes across disciplines and across different substantive subfields in political science, right? We can think of outcomes like like whether a war is fought or not, whether there is an onset of a civil war or some other type of ethnic conflict, for example, as a dichotomous outcome. If we're interested in, comparative politics, we might be interested in when governments end or dissolve versus not, right? That could also be modeled as a dichotomous or binary outcome. If we're interested in political behavior and political attitudes, thinking about outcomes like turnout and voting behavior, these outcomes can also be oftentimes measured as binary responses. Or if we're studying political institutions or political elites, whether members of parliament vote in favor of a certain proposal or against a certain proposal. Again, we have a dichotomous outcome where we're interested in predicting or finding predictors, finding variables that are associated with predicting either a vote in favor or a vote opposed, or whether or not the probability for the onset of conflict is increased versus not, right? So across disciplines, there are a lot of outcomes, a lot of phenomenon that we can ultimately think about as binary, as dichotomous, and where we're interested in factors that affect the probability of observing one value versus another value. Okay. And so based on our discussion that we had so far, focusing on OLS and how to measure continuous outcome variables, the first obvious question is, okay, we have that kind of that tool in our toolbox. So what happens if we run OLS in such a situation where our outcome is not actually continuous, but is just binary? Okay, and it turns out OLS in many circumstances actually works quite well, and we can actually, at least as a first step, oftentimes just look at an OLS estimate in the context of binary outcome measures. Okay. And as soon as we use OLS or a linear regression model with a dichotomous outcome measure, what we're working with is what is called a linear probability model. Okay, I'm going to talk a little bit more about why we call it a linear probability model later on. But to kind of introduce this idea, keep in mind that whenever we're talking about linear regression and kind of interpreting linear regression coefficients, what linear regression ultimately does is it gives us basically predictions of conditional means for specific values of your set of predictors. Okay, and usually we thought of this as conditional means in the context of a continuous outcome measure, right? But now we have a dichotomous outcome. Okay, now we have a variable, let's call it yn in our case, that is either 0 or 1. Okay, so that would be a simple Bernoulli trial with some success probability pi. Okay, what is the conditional average, or what is the average of such a dichotomous outcome measure? Well, if we kind of look at the expectation of a Bernoulli random variable, all we have to do is basically multiply the probability of yn being equal to 1 times 1 plus 0 times the probability of yn being equal to 0, okay? Which is a quite trivial equation, because obviously it reduces to the probability of yn being equal to 1, okay? This is just a a way of saying that the expectation of a dichotomous random variable is equal to the probability of success of observing a 1 rather than a 0. Okay, if I have a vector of dichotomous outcomes and I compute the average of that vector, I get an estimate of the probability of observing a 1 versus a 0. Okay, so that's pretty straightforward. And ultimately what OLS allows us to do, under making certain assumptions that we already talked about regarding linearity, and other assumptions regarding kind of the error term and so on, what we get is ultimately a conditional expectation, and that conditional expectation can be interpreted as a probability, just like the expectation of a Bernoulli can be interpreted as the probability of success, okay, of observing a 1, okay. So in the linear probability model, the reason why we're kind of calling OLS used with dichotomous outcome measures the linear probability model is because we basically use our linear model to directly model the underlying probability of observing a 1 versus observing a 0, right? So in other words, we're looking at a conditional expectation, the expectation of our dichotomous outcome variable yn, which, as we said, is equal to the probability of yn being equal to 1, which for short we just call pi n for now. And we just make the assumption that we directly kind of model this in a linear fashion as beta prime xn, so as a basically linear combination of all our predictors and our OLS coefficients. Okay. So ultimately, that means, of course, that the probability of observing a success in this linear probability model is constant in the predictors, right? So a 1 unit increase in x or a 1 unit in x1 or a 1 unit increase in x2 and so on always leads to the same change in the predicted probability of observing a 1, okay. And on the one hand, this gives the linear probability model the advantage of being very easily interpretable, okay. We can directly interpret the coefficients on the probability scale, so to speak, in terms of changes in probabilities, okay. But it also leads to certain disadvantages, right? Because ultimately, and we'll get to that in the following slides, that can lead to ultimately predictions that are outside of the range of outside of the range of outcomes that we actually should observe, right? Probabilities are bound between 0 and 1. And if we just make this linear assumption directly relating the probabilities to our systematic component, beta prime xn, in theory at least, we can get predictions of probabilities that are larger than 1 and smaller than 0. And obviously that doesn't really make sense. That cannot really correctly characterize the underlying data generating process, okay. We can also, of course, specify the variance of a simple Bernoulli random variable and plugging in our systematic component beta prime xn. We can kind of simplify that, and the key point is that we can use OLS with binary outcome measures. We could go kind of through all the assumptions to, for example, show unbiasedness. We've done this before without making without talking about dichotomous outcome measures. But the key point is that OLS, even if our outcome measure is dichotomous, OLS is still unbiased. Okay, we're still getting an unbiased estimate of the conditional expectation of our outcome measure depending on our predictors that are included in our model, right? And it turns out that this conditional expectation of a dichotomous outcome measure is equal to the probability of observing a 1 rather than a 0, okay? So we can still use OLS and we still get unbiased point estimates for beta hat kind of the linear effect on the probability of observing a 1 rather than a 0 in our outcome measure. Okay. But of course there are problems, right? There are reasons why we don't just always use the linear probability model, and why people prefer logit and probit and other types of models, okay? One of the problems that you have with the linear probability model, even if you can show that OLS is still unbiased when kind of the outcome measure is still is just dichotomous, by definition, you know that other assumptions that we usually make in the OLS or in the linear model that we talked about, they don't hold anymore. And one of those assumptions that doesn't hold anymore by design is this constant error variance assumption. Okay, so by virtue of having just two different outcomes, 0 or 1, basically by design, if you run, or if you specify or if you estimate a linear model, then that model cannot have constant error variance, right? So you always have heteroscedasticity. Now, what is the effect of heteroscedasticity? As we talked about, heteroscedasticity by itself doesn't really jeopardize our point estimates for our parameters, but it ultimately leads to incorrect and inflated standard errors. Okay. This is kind of just the explanation of why we always have heteroscedasticity. Because our outcome is always just 0 or 1, that means our errors can only take two different values, 1 minus beta prime xn for observations that are actually equal to 1, and minus beta prime xn for observations that are equal to 0. Okay, and so as we can see, the errors are now always basically a function of xn. Okay, and so therefore we have heteroscedasticity, we have non-constant error variance that is correlated with the axis. Okay. So the underlying problem here is that inference from OLS is not valid, at least not with kind of additional, robust standard errors or weighted least squares or something like that, in order to account for this constant error variance. Okay, so we have non-normal heteroscedastic errors. Okay, so whenever you use a linear probability model in kind of the classic frequentist sense, you do have to take into account this issue of heteroscedasticity and use, at least at a minimum, use robust standard errors. Okay. To kind of just illustrate this linear probability model with a quick example, I'm gonna use the example that we have a whole other video later on using logit and probit, which is modeling political preference given income, which is one of the examples that was also discussed in our required textbook. And this is a really large data set with a lot of variables, a lot of years. So feel free to just also take a look at the data and maybe run some other models with other outcomes that you would be interested in, or other predictors that you would be interested in. Okay, this is a cumulative file of the American National Election Studies. So these are all election studies for presidential elections. Over a number of years, starts at 1952, goes all the way to sometime in 2000. I don't know exactly whether it's 2008 or 2012, but you can find out just by looking at the information in the data. Okay. For this specific example, we're just going to look at the election, the 1992 presidential election between Clinton and Bush. So we're filtering out that specific year, we're saving it as a tibble, and you can see we have, in the whole data set, we actually have 34,000 observations, so 34,000 respondents and 70 variables, right? So there's a lot of stuff in there. I'm just looking at one specific point, but I still wanted to upload the whole data so you can, play around and try some alternative model specifications as well. Okay. So suppose we want to now explore, kind of predict vote choice in presidential elections, specifically in the 1992 US presidential election, based on personal income. So based on, there's a measure of household income. It's a 5-point measure, basically different income brackets, income groups, and we're just looking at kind of the bivariate relationship, how income levels are associated with support for the Republican candidate, so vote for Bush in this case. Okay, the way I'm going to run this now is basic in base R using the the LM function. No, no stan, no Bayesian statistics. We're just using a basic OLS model to run this linear probability model. Okay. And so the way we set this up is just bivariate. We have our vote. This is our vote choice for a Republican candidate that is equal to 0 if it's not Republican, 1 if it is equal to if the person voted for the Republican Party, and income is our only independent variable, only predictor. And obviously we would need to control for other potential confounding factors, but just go through the basic model. Okay. The data is the subset, so we're just looking at the ANES from 1992. Okay. And what we see here is a basic regression outcome. We have our intercept, and that is 0.16. So we can interpret this intercept as the expected percentage of, or the percentage of voters who support the Republican candidate, conditional on income being equal to 0. Okay. Now remember that this income measure is a five outcome measure that ranges from 1 through 5. Okay, so obviously this 16% kind of expected support for the Republican Party is already an extrapolation outside of the range of income that we actually observe in the data. Okay, so it's not very informative. Okay, what is more interesting is the income variable, right? The income or the coefficient for income, and we can again interpret this OLS coefficient the same way we interpreted OLS coefficients in the past, just keeping in mind that the conditional expectation of our outcome measure can be interpreted as the proportion of ones versus zeros in our outcome. Okay, so this means in this specific model we can interpret this 0.05887 as comparing two different respondents, or two groups of respondents, that differ in their level of income by 1 unit. So basically that where one set of respondents has a higher income bracket, one higher income bracket than the other, this model predicts that the expected vote share for the Republican candidate, for Bush, is about 5.8 or about 6 percentage points higher among the respondents with the higher income bracket, in expectation, of course. Okay, so obviously we can't give this any causal interpretation, but we can still think about this as a comparison between groups of voters that are included in our data. Okay, we can also directly plot this to kind of think about this interpretation. Okay, and this is kind of similar to the plot that is also included in the textbook, so you can kind of replicate this as well. Again, the code for this is also on our Studio Cloud, and just let me move myself out of the way here, up here. Okay, that's better. So what we have here, of course, is 5 different income groups from 1 through 5, as I mentioned, and we have either 1 or 0 for respondents who supported the Republican candidate, who voted for Bush, versus 0 who did not. Okay. And basically the regression line that we fit through these, and I should mention that of course I included a random jitter around these points in order to give you a better idea of how many observations are in each of these fields, right? So they wouldn't just all sit on top of each other. I added some random noise on top of that. Okay. The key point here is, of course, that basically making some additional assumptions about kind of most importantly, this linearity assumption, we now, by virtue of estimating this OLS model, we now have a basically estimate of the conditional expectation for each income bracket, which is the probability or the proportion of votes for Bush versus votes for Clinton in that specific election. Okay, so overall, this seems like a pretty good, a pretty good model, a pretty good option for dichotomous outcome measures. We can directly interpret the coefficients as changes in probabilities or comparisons in probabilities. But obviously there are problems. One we already mentioned, which is related to this issue of computing the correct standard errors, is considering that we have heteroscedasticity by design. And the other component is that in this model, where the proportions of vote for the Republican candidate are obviously not too far away from 0.5, okay. This model is actually quite reasonable and gives us reasonable predictions for across the entire range of income. But in theory, one big problem is that the linear probability model can yield out-of-bound predictions, right? So in other words, if we had a larger range of income that we would look at, or a stronger effect of income on the Republican vote share, we could end up with predictions that are basically below 0 or above 1, which then kind of don't have this nice interpretation as kind of direct conditional expectations that we can interpret as percentage of ones or percentage of zeros conditional on our predictors. Okay, so in order to kind of solve this issue of out-of-bounds predictions, as well as solving the issue of how to exactly quantify the uncertainty around our estimates, we need to transform the systematic component beta prime times xn with some link function that ultimately maps this linear systematic component that ranges theoretically from minus infinity to plus infinity into the range of probabilities, which just range from 0 to 1, right? So instead of having our beta prime xn as the direct linear probability model, we want to find some function g that maps that linear predictor that we use onto a range that is between 0 and 1, okay? And so how we do that and what different functions we can use for g of x is going to be the topic for the next video, where we're going to talk about logit and probit models, which do exactly that, which kind of provide this link function to prevent out-of-bound predictions. Okay, but I'll take a break here and then we'll continue with the next video in a second.